Now it's time to get into the fundamentals of the science that we're dealing with. The most critical of that is understanding the arithmetic. This is science after all, and in science we measure things. And in astronomy, we measure astronomic numbers. Let me tell you what I mean. In the last lecture, I made mention of this little formula. P squared equals 4 pi squared times a cubed over gm. Now, in a few weeks, you're going to have to wrestle with that formula. You're going to have to plug in numbers to make that formula work. And I'll give you an example of the kinds of numbers that you'll be dealing with. Now, just to remind you, this is Newton's version of Kepler's third law. It tells us what the period is in time of an orbiting object given its distance from its primary, that would be a, g, gravitational constant, the universal gravitational constant, and m, which is the mass of the primary. So let's just plug in the numbers that would be associated if you were to calculate the period of one lunar orbit. So pi is pretty straightforward. A, on the other hand, is going to be expressed in meters, and so A would be 384,000 kilometers. That's the distance from the Earth to the Moon, which comes out to 384 million meters. G is the universal gravitational constant. It's a number that reads this way. And m would, in this case, refer to the mass of the Earth. So there we go. Those are some astronomical numbers, and they're pretty ridiculous. And good luck plugging these numbers into that formula. You'll choke. And most calculators won't even go that far. So we need to use scientific notation. So we're going to spend the next hour or so going through scientific notation. You may already be familiar with it, but we're going to go a little bit beyond what is normally taught in the public schools. You have to be able to actually use it in different operations: adding, subtracting, multiplying, dividing, squares, square roots, cubes, and cube roots. So if you're already a whiz at this, relax and enjoy the easy A. And if you're a little bit rusty with this, well, this is the time to get back up to speed on this. So we'll go to page 6 in the lab manual. So just follow along with the lab manual. Page 6, topic 1, lab 1, scientific notation. Scientific notation provides a means of managing and calculating extremely large and extremely small numbers. Just plug that right in. extremely large and extremely small numbers, and it is based on an understanding of basic algebra and the decimal system. All right. What is the decimal system? Well, the decimal system is the base 10 system. And since you're in college, now you should know who invented the decimal system. And it was not Dewey. That's the library guy. The gentleman who invented the decimal system was a fellow by the name of Ugg, the caveman. You know, you never learned that in school either, did you? Well, here we go. What about Ugg the caveman? Well, Ugg the caveman, who lived in a cave, because after all he was a caveman, woke up one morning in his cave, stumbled to its entrance, and scratching himself rather indelicately, which is what cavemen did in those days, gazed out upon the Serengeti, where a herd of wildebeest was thundering by. And it was at that moment that Ugg, the caveman, had his epiphany, his aha moment. A wildebeest thundered by, and Ugg went, huh. And a second wildebeest went by, and he went, huh, huh. And the third wildebeest thundered by, and he went, huh, huh, huh. And he kept on going to all 10 of his phalanges, and then he looked down at his feet, which were encrusted with that which we would not mention in polite society, so he stopped there. We should be thankful, because otherwise we would have a base 20 system. We're reasonably sure that Ugg, the caveman, was a young caveman. Why, you may ask? Well, had he been an older caveman, the odds were pretty good that at some point in his life, some critter would have bitten off one or more of his phalanges, and we'd have wound up with a base 9 or a base 8 system. But we didn't. We got a base 10 system, courtesy of Ugg, the caveman. There. Aren't you glad you're going to college? Look what you've learned already. Now, on the page you see this algebra-looking thing. And beside it you see this scientific notation-looking thing. And we're going to cheat just a little bit, because there is, in fact, a one-to-one correspondence in the pieces and parts that we see here. So, what's that? Well, that's an exponent. And so is this. This is the base. And here's where we're going to cheat a little bit. We'll call this the base as well. And this is the coefficient. All right. They work in exactly the same way. Unfortunately, this scientific notation is frequently not taught alongside this basic idea in algebraic notation, and it's too bad, because they work in exactly the same way, and that's what the next fill in the blank here is. Right below that, the same rules pertaining to exponents, bases, and coefficients. Write that in there. The same rules pertaining to exponents, bases, and coefficients in scientific notation also apply in algebra. They work the same way. Now, we're going to redefine what these pieces and parts are. First, we'll start with the coefficient. What is a coefficient? Well, in cheap, sloppy language, a coefficient is this. How many you got? That's it. Don't make it any more fancy than that. That's all a coefficient is telling you, is how many you got. Okay? The base. And again, don't make it any more complicated than this. It's what you got. What you got here? Tens. How many? 3. What you got here? X's. How many? 3. What you got over there? Ducks. How many? 3. So we're just counting ducks, chickens. Now we get to exponents. Now, we're going to redefine an exponent. And I don't care if you're already a math major from MIT. I want you to take whatever definition of an exponent you have and kick it to the curb for the next 15 weeks or so. Here in this course, we're going to define an exponent as this. It's an instruction. And when I stomp, that means that's heap big important. Don't you forget it. This is going to be critical. It's an instruction. That is going to help you along, and you'll see. Okay, so we'll go to the next page. Page 7. Okay, we'll start with something that everybody's pretty familiar with. Positive exponents. Positive exponents usually aren't a problem. So we'll start there. This is the easy stuff. So let's say that I have x to the third power. All right. Now, remember, that is an instruction. That exponent is an instruction. It's telling me to write down x 3 times and multiply them. That's what the instruction is. Now at this point, I need to pause and address the gorilla in the room. There are any number of folks out there who never got warm and fuzzy over the idea of x's and y's and a's and b's being numbers. I want to take the mystery out of that for you. There are 2 and only 2 reasons that we use x's and y's and a's and b's for numbers. The first one I call the Ozzy Osbourne reason. All right, are you ready? Here it goes. I don't know. Exactly. I don't know. Mathematicians are egotistical. They would rather burn at the stake. They would rather have their teeth drilled than to ever have to stand up in a room full of people with their faces hanging out and utter the words, I don't know. And instead, they will say something like, well, based on the parameters that you have articulated, the only possible outcome would have to be X. And everybody else is supposed to go, ooh, he's educated. No, he's not. He's clueless. So that's what X is. I don't know. The other reason that we use X or Y or A or B is what I refer to as the Lewis Black reason. So here we go for the Lewis Black reason. Ready? I don't give a shit what the number is. That's it. Either I don't know or I don't care. Those are the only reasons we use X or Y's or A's and B's. I don't know or I don't care. Don't make it any more fancy than that. So now, staying with positive exponents, we'll try another one. Let's try this. X to the third times x squared. What does that equal? Well, back when you took algebra with Mrs. Gilhooly in high school, she said, well, what do? You add the exponents. And the answer is x to the fifth. And why is it x to the fifth? Because they told you to. All right? Well, again, remember, what is an exponent? It's an instruction. So, this instruction is telling me to do this. This instruction is telling me to do this. Count them up. Yeah. X to the fifth. It's nothing more complicated than that. Now, usually folks are pretty good to go with this part of it. I don't think anybody's getting a brain hemorrhage yet. Now we'll talk about negative exponents. Negative exponents is where people start to get into hot water. So that takes us up to page 8. Now the way we're going to get to negative exponents is we're going to sneak up on them just a little bit. So let's look at this idea. Let's say x to the fifth over, or as we say here in Maine, over x to the third. Now we're dividing. What do we do when we divide? Well, we subtract the exponents. Why? Because they told us to. And the answer becomes x squared. Okay. Again, remember, an exponent is an instruction. Let's follow the instruction. What's really going on here? X times x times x times x times x over x times x times x. And what can we do here? Well, we can cancel. And our answer becomes x squared. That's pretty straightforward. But now I'm going to throw you a curveball. Same page. Let's try this. X to the third over x to the fifth. All right. What do we do with exponents when we divide? Well, we subtract them. And so the answer winds up being x to the negative 2. What the hell's that? Well, again, let's follow the instructions. What we're really saying here is x times x times x over x times x times x times x times x. What's the one number I can multiply anything by without changing it? Well, 1. So I'm going to multiply this top row by 1. Why? Because I can. All right. Now, we can cancel. And our answer becomes 1 over x times x, x squared. So now the question is, which one is it? Well, I'll remind you of something else that Mrs. Gilhooly told you in high school algebra. See if you remember this one. If A equals B and B equals C, then A equals C. Remember that? So we got the same sort of thing happening here. This equals this, this equals that, and that equals that. Therefore, guess what, boys and girls? This equals this. All right? It means the same thing. It means the same thing. It's just written differently. It's no different than I can write this or I can write this. They mean the same thing. They're just scribbles of ink. Don't make them any more fancy than that. So, with this in mind, then, we can say if I have A to the negative 3, that would be the same as 1 over A to the third power. If I have 1 over 10 to the fifth, that is the same as 10 to the negative 5. If I have x to the negative y, that is the same as 1 over x to the y power. Now make a note to yourself. Make a note to yourself on this page somewhere so you don't forget it. A negative exponent does not mean a negative number. I'll say that again. A negative exponent does not mean negative number. All it's doing is, all that negative sign is doing is just modifying the instruction. That's it. It's telling you to turn it into a fraction. So in other words, the bottom line here is a negative exponent means that you're dealing with a fraction or a decimal. Write that in there. A negative exponent means you're dealing with a fraction or a decimal. That's all. Page 9. Okay, page 9, we have to talk about the 0 power. Okay, so any non-zero number to the 0 power equals, write this in there, 1. not 0, 1. Any non-zero number to the 0 power equals 1. Again, let me show you why. So, if I take this number here, okay, that over that equals 1. No big surprise there. How about negative a squared b to the third c to the fourth over negative a squared b to the third c to the fourth? It equals 1. Doesn't matter what the number is. It could be Flizzle-widget divided by Flizzle-widget. The answer is going to equal 1. So with that in mind, let's try this. We'll use x because I don't care what the number is. Let's say I've got x to the fifth divided by x to the fifth. And we know that equals 1. But wait a minute. What do we do when we divide and we're using exponents? What do we do with the exponents? We subtract them. So x to the fifth over x to the fifth, we subtract the exponent. It also equals x to the 0. And again, if a equals b, b equals c, then a equals c. This equals this, and this equals this, therefore this equals this. All right? So it doesn't matter what the number is. I can have what's that equal? 1 all day long. Okay? It's a very handy tool. We're going to use 10 to the 0 power as a way to get us out of the forest from time to time. X to the 0 is very, very handy. So 10 to the 0 also. Just remember, 10 to the 0 equals 1. 10 to the 0 equals 1. Just remember that. First power. On the same page. Any number to the first power equals itself. Nothing more fancy than that. Remember, an exponent is an instruction. It's telling you to write the number down once and leave it alone. Okay? So any number to the first power equals itself. Finally, at the bottom of the page, you see something about standard notation. What is standard notation? That's just a plain old bare naked number like you've been using all along anyway. It's just a fancy way of saying plain old number. That's what standard notation is. All right. At this point, I'm going to ask you to hit pause and go to page 10 and take a few minutes and do these lab exercises. And go ahead, give them your best shot. This is a good way to get started on re-evaluating using exponents. So, assuming that you've hit pause and you've done the exercises on page 10, let's go through them. The first one, 3.8 to the 0 power. That equals 1. 3.8 times 10 to the 0 power, well, that winds up being 3.8 times 1, and so the answer is 3.8. 3.8 to the first power is 3.8. 5 to the third in standard notation, that's 5 times 5 times 5. 5 times 5, 25 times 5, 125 is the answer. Okay. 672 times 10 to the third. 10 to the third, that's 10 times 10 times 10. That's 1,000. So 672 times 1,000, 672,000. 6 to the negative 2. Two possible answers here. That can be 1 over 6 squared or we can do this, 1 over 36. Either way will work. All right. In the expression 3.12 times 10 to the fourth, the 3.12 is called the coefficient. (9.36 to the -1). I threw that one in there as a little bit of a curveball. The answer is 1 over 9.36. Not negative. Not negative. Then we have x to the 5th times x to the 7th. The answer is x to the 12th. We have y to the 6th divided by y to the 4th. The answer is y squared. (53 to the 0 power), that equals 1 all day long. 87 to the 1st power equals 87. 2.38 times 10 to the 0. 10 to the 0 equals 1, so the answer is 2.38. Definition of an exponent, don't you ever forget it, it's an instruction. In the expression 8.75 times 10 to the 7th, the 10 is called the base. A negative exponent indicates you're dealing with a fraction or a decimal. And 5 to the 15th times 5 to the -17. Well, there are several possible answers. It can be 5 to the -2, or it could be 1 over 5 squared, or it could be 1 over 25. Or it could even be 0.04. They all mean the same thing. All right, so that's the basic intro. We'll stop here and then go on to the next topic.